You're going to come up here and join my class. Give me one moment here. I'm just taking roll really quick with the names that are posted. Got it. Did he come by just now?
It was just about 20 after 7. He said, I'll be there in a few minutes.
Okay.
So I put it out on the front porch and said, it's on the front porch. The rest will keep till you get here.
Okay. Bear with me just for a moment. I'm just taking a quick roll of who's here online. First, before I say anything, are there any questions or concerns?
I have a question.
Go for it. Jade, I know you have questions for me. I knew that.
Yes.
Go ahead.
I'm also as well as lab. I know the last time I had spoke to you for last week, since this is only...
Was this for lab or lecture?
No, it was for lecture.
Okay, all right.
Yeah, the problem that I was emailing you with, that was about lecture. I'm also really confused on how to get into lab. I cannot figure it out. I know the last time you had gave me the actual Zoom number, but I had typed it in.
He said you got in. Did you not get in?
I did with the number that you had given me for the Zoom. I just, since you had gave it to me and I typed it in, by the time that I had hit okay, I didn't get a chance to write it down. So I don't know how to get in either.
Can I give it to you after class?
Yes, that's fine.
Okay.
That's fine. Yes.
Because I'll have to search for it. I think I'm not, did I text it to you? Is that how we did it?
You had called me because I was like already late. I couldn't figure it out.
Okay,
and
but it was via phone or phone calls, correct?
Phone call, correct.
Okay, all right, yeah, I'll have to search for it in my list of messages on my phone, but
okay.
That's easy to do.
Okay, thank you.
Yeah, I understand. I think, have you tried for anyone else who's struggling to get into lab, because he was telling me that someone who's also here today was also not in the lab on last week. And Jade, it wasn't you, it was 2 other people.
Yeah, because I did attend.
I think there's that Zoom link, and bear with me as I'm continuing to make a roll here of the students who are here today, because it's needed for your student loan information. Bear with me. Ariana, Wendy. Okay. I think I got the majority of people here. Jade, when you have gone in, do you see that when you go in,
Which is syllabus, correct?
no, let me show you where he's posted the link. That's the way you go into lecture. When you go in, bear with me just for a second here, my mind is not, I'm working on being a better morning person, but I'm really not. In a lot of ways, as my roommate smiles in the other room and laughs. Right here, there's a Zoom link. Have you tried clicking on that and getting into lab?
I have not tried that way, no. So it's just
that's a possibility.
Okay. I think that's what I had the last time or something, and it ended up being wrong because I had known I'd struggled to get into your class as well at first. And then that's the first time that I had spoken to you and you had to give me a different Zoom number under. So I'll try that way to see if
no, you know what? I thought he posted this because I don't remember posting this. He may have posted it. And now that I'm looking at it, it says it's lecture. It probably is. Let me look one other place because I know he put it somewhere. Give me 1 second here.
I wrote it down. It's under
Is it under lab stuff?
Yeah, if you go under that.
Oh, okay.
Under announcements?
Yeah. No, go down to, I think it's syllabus.
Syllabus, that's why. Okay.
Syllabus. What about Zoom?
Oh, wait, right there. Right there. It's announcements, Zoom meetings.
Okay. So click on this.
And then there's the number.
Do you see this?
Thank you.
You're welcome. See if that works. And like always, if you can't get into your lab, let me try. I can the other thing is I can email Dr. Weeks and ask him let him know that one of you weren't able to attend.
Okay.
I know you can do that, but I can do it also.
Okay, thank you. I appreciate it.
You're welcome. She's good, Mom. She's good just like that. She'll stay up there. You don't have to create her. She'll stay up there. I'm sorry. My mom, who's my roommate, is leaving, and she's going to create our little dog here. And I honestly like having them out and about. And so I just told her, I said, she's good just where she is. She'll sit here and sleep throughout my class. Other questions or concerns? I think if I remember right, we're starting chapter 2. Is that correct?
Yes.
Okay. So remember that for every chapter that we do, you'll have one chapter practice that you need to do, one chapter quiz that you need to do, and one smart book assignment. For the smart book assignments, your grade will be based on completion. If you do it, you get 100%. If you don't do it, you get some level of completion grade. If I remember right.
When was that due?
I think the smart book assignment was due today, but I can extend it out if you need me to.
Oh, please.
I think it was due last night.
Oh,
great.
Okay.
Oh, yeah.
That's what I struggled with as well, that's what I was also emailing you about, was the confusion of me getting the quiz done, which said it wasn't until the 16th. And I ended up finding out that it was the quick book assignment and I can't find the quiz.
Okay, so if you look right here
on the side,
this gives you the due dates. And actually it says the chapter 1 smart book assignment isn't due until next week.
Yeah.
Okay.
So this will tell you when things are due.
Okay.
It doesn't say smart book on it. You'll see that.
Okay.
And I may Yeah. The chapter 1 quiz is due that same day.
On the 15th or?
You know what? I don't know why it has it on the 15th and 16th. It has it assigned 2 different times. But you can do it on either day. I'm not sure what's going on there. I don't know why it has it posted there. That sounds like a glitch to me. But I can't fix it because it's a computer glitch. Bear with me here as I come back to it. So I would think it would be the 16th because that sounds more correct to me. So chapter 1, the Smart Book practice isn't due then. I would do it at the same time. It isn't due then because it's open until we take the first exam.
October.
That's the reason the due date is so off on that one. Down here.
Mhm.
So for every chapter that we do, you're going to have 1 Smart Book assignment, 1 practice, and 1 quiz. And the practice you can do over and over and over again up until the first exam. And your highest score will be the one recorded. Other questions?
In the exam, you get 2 chances, right?
Yep. And the same for the quiz.
You could do them back to back?
Yep. Wait, the exam and the quiz, or the practice and the quiz?
Exam and a quiz.
No, because the quizzes are due in a week. The practices you could do back to back.
Okay.
The exam hasn't even been opened yet. Does that make sense, Casey?
Yes.
Okay. So let's get started with chapter 2 today. So the chemistry of life. Why do we even need to talk about chemistry in this class? The reason is, I'm sorry, bear with me just for a second here. The reason is, one second, is because if you remember, we talked about how biological life is a hierarchy of complexity, where we start with atoms and elements. We move into macromolecules. From macromolecules, we create organelles. From organelles, they interact and start to function as cells. Cells interact, and identical types of cells start to function as tissues. More than one tissue type can come together to form an organ. Organs come together to form organ systems. And organ systems interact to form a whole organism. So the basis of all physiology and biology is chemistry. We often call it biochemistry because chemistry can involve living and non-living elements. So to distinguish chemistry with regards to biology, life, we call it biochemistry. Basic principles. The science and structure. Chemistry is the science and structure and interactions of matter. Matter is anything that occupies space and has a mass. If you think of mass as being a volume, anything that occupies space and has some form of substance, mass. The states of matter are a solid, a liquid, and a gas. The amount of matter a substance contains is its mass. Let me back up just for a second. So matter is anything that occupies space and has a mass. Mass is the amount of matter a substance contains. So for example, how much area or volume does that take up? That's the mass. Weight, a mass's weight is the force of gravity that acts on it. If you think about astronauts that go up into out into space, when they're out in space, their mass does not change. Their volume does not change. However, their weight changes drastically because the force of gravity diminishes. Chemical elements are unique substances that cannot be broken down into simpler substances by normal chemical methods. So we can't heat them and break them down. We can't cut them up and break them down. We can't boil them and break them down. We can't blend them up and break them down. We can't heat them up and break them down into something more simpler. So chemical elements are unique elements that cannot be broken down into simpler methods. Bear with me. So a chemical element is the purest substance, and it consists of only one type of atom. We're going to talk about atoms here in a few minutes. But a chemical element consists of only one type of atom. We can have a lot of one chemical element But when we refer to that chemical element's mass, all of its mass is one type of element. There's only one type of element within that mass of a chemical element. There are 91 naturally occurring elements on the earth. 24 of these play normal physiological roles in the human body. And they're listed here on this, in this table here. Six of those elements make up 98.5%. Oftentimes we refer to as 98.6, somewhere in there, are the elements that make up the body weight of an individual. The lesser elements, sulfur, potassium, sodium, chlorine, magnesium, iron, 0.8% of the total body weight. And then we have trace elements. Several elements that make up our body, human bodies, are called minerals. These are inorganic elements, and we'll talk about the difference between inorganic and organic here in a moment. But inorganic elements that are taken in via our diet. They make up approximately 4% of the human body weight. 75% is calcium, and of this 4%, 75% is calcium, and 3% is phosphate. 25% is chlorine, magnesium, potassium, sodium, and sulfur. And as you look, these are also listed over here. So calcium and phosphate make up 3% of the human body weight. So 3/4 of this, 3% of our human body weight. 1% is chlorine, magnesium, potassium, sodium, and sulfur. If you want to think, recognizing this is only 4%, you may not think that's really a major part. However, these have very, very important functions. We have crystallized calcium and phosphate, magnesium, chlorine, and sulfur ions in our bones and in our teeth, help maintain the structure. If you remember, we talked a lot about structure and function and how they relate. Minerals are very important in maintaining structures. Proteins commonly contain sulfur. Phosphate is a major component of nucleic acids, adenosine triphosphate, which we'll talk about maybe today and definitely next week if we don't talk about it today. Cell membranes, enzymes, and other organic molecules that also require minerals to function. Of this trace element, so this was that 0.07% or 0.04%, the bottom part of that table, are required to prevent disease. An iodine deficiency, one of the trace elements, prevents production of thyroid hormones, resulting in a goiter. If you look at this woman's neck over here, do you see the enlargement there?
Mhm.
That is what they call a goiter, which is because the thyroid gland, which is right there, when your body is not producing enough thyroid hormones due to an iodine deficiency, trace metal element deficiency, your thyroid will enlarge to try to compensate and try to make more. What in our diet, you don't see a lot of goiters in the US population. I don't think, I'm trying to think if I've ever seen one. Why do we not see them?
Because we have that in our diet almost every day.
What is it in your diet? What brings
Sodium.
it into your, what?
I don't know. Is it sodium?
You're close. You're very close, actually.
Yeah, I just.
What about, how about we just say salt?
Yeah. Sorry.
You're right. You're exactly right. Because one thing that we have is we have iodized salt. If you bear with me just for one moment, I'll be right back. Evan, you're all right, buddy. Evan, it's all right. Evan, it's all right, buddy. If you look, you can kind of see it. Iodized salt. The reason they started adding iodine to salt was to avoid iodine deficiencies in the population. Normal sea salt is sodium chloride. The difference between iodized salt and sea salt is the chlorine in iodized salt is substituted with iodine. Without iron, your body cannot transport oxygen. If you have ever heard of someone becoming iron anemic.
That's me.
Yep.
Okay, I think a lot of us have, because it can be very popular among women.
Mm-hmm.
I had a student in another one of my A&P classes that had pre-surgery and post-surgery anemia. What is it due to? If you heard people becoming anemic. Paisley, stop.
Makes you really tired.
It makes you really tired. Why do you think it would make you really tired?
Because your body's not getting the oxygen that it needs. And it's also,
go ahead.
I think your red blood cells are low.
Your red blood cells are low. Your blood flow is low. Your red blood cells are low. Your blood flow is low. And since your blood flow and your red blood cells are involved in your oxygen and carbon dioxide transport, it's also involved in maintaining your nutrient level, because that volume, the blood volume, is crucial. So the first thing that they do when people are struggling with any form of anemia is start asking them to take an iron supplement. I know that I was diagnosed, growing up, I had a lot of surgeries. I don't know if I've talked about this, and I'll talk about it probably later in the semester if I don't talk about it now. I had a few birth defects, and I had a lot of surgeries growing up. And at one point, when I was right around in my older teens, every time they do a surgery, they do a blood draw right before.
Mm-hmm.
And they diagnosed me as being anemic. And so from there on out, I've always taken an iron supplement. And I can say that when I don't take it, I don't feel as well. I actually am more prone to getting sick, and it doesn't take much for only a couple days without an iron supplement, and I start to not feel as well. So I don't know if that part of that might be mind over matter, but I've just gotten used to taking it on a regular basis. And so these are trace elements. So these are really small percentages, but they're obviously crucial for your well-being. Fluoride is another one, usually added to municipal water and dental products to help reduce tooth decay. Any questions about this?
I learned something over the summer. I took a nutrition class, and they fortify a lot of the cereals. I guess I never really thought about a whole lot about why they call them fortified cereals. But they put a lot of these things like into the cereals to also help the population, like the way that they put the iodine into the salt as well.
Right.
So that kids and stuff in this country don't have as many, to help them out as they're growing up.
Yeah, if you notice, you don't see in our society, and we'll talk about this a little bit when we talk about bones. Do you see rickets very often?
No.
We know that not every parent is completely aware and alert about what their child is eating all the time. And it's a vitamin C deficiency, which is what results in rickets. So like—
What is it called?
Rickets, Rickets. We will talk more about it in a couple of weeks here. But it's a vitamin C deficiency. And like Catherine was saying, if you think about, it's Catherine, right? Okay. Like Catherine was saying, if you think about another one, vitamin D in your milk.
Mm-hmm.
Because it's very important in the absorption of calcium. So if you're drinking a lot of calcium, but you can't absorb it anyway, what's the point of drinking a lot of it if it's just going to get excreted because you can't absorb it anyway? Great. So when we talk about chemical elements and trace elements and minerals, the basis of all that is the atom. Atoms are the building blocks of elements, and they are composed of subatomic particles such as protons, neutrons, and electrons. The protons and neutrons are contained within the nucleus of an atom. The protons have a positive charge. The neutrons have a neutral charge, and the electrons have a negative charge. The electrons orbit around the nucleus. We draw them so that they look like they're kind of orbiting like in a planetary model. We draw them so that they look like this. However, electrons are so small and so minute in their mass in comparison to the nucleus, which is also, you know, we honestly, I had a student ask me last night, how do we know that this is the case? Have we actually ever seen an atom? I don't think we've ever seen an atom. As far as I know, they've never actually seen one. A lot of this is theoretical physics, but the experiments that have gone on support the theory. I have a beaker here that I own that was part of the Philadelphia Project. And if you're familiar with the Philadelphia Project, that was the creation of the atomic bomb. Actually, because I'm home, this is one of the advantages of being home and teaching. Give me 1 second there. So this, stop sharing just for a second. Got to do a little bit of show and tell every once in a while when you do online classes. If you look at this, this is a beaker that was used in the lab of when they developed the atomic bomb. So for me, it's a family heirloom that one of my grandparents purchased a long time ago. And it was given to me because I'm the scientist of the house. And so if the atoms do not exist, how do we know that the atomic bomb works? Because what they did with that is they collided a lot of bombs they collided a bunch of atoms together that blew apart and create all sorts of havoc. Because they're essentially blown apart. So have we ever seen an atom? No. Do we know that theoretically they probably exist? Yes. Because we've blown them apart. So when we think about this atomic theory, it's kind of like the theory of evolution. It's kind of like the cell theory, that all cells come from pre-existing cells. We don't know for sure that that's the way it is because we've actually never seen it. But all of the experiments that have occurred that people have used to study the atoms have always proved that this is probably the correct structure. I'm going to put this back because it honestly is pretty valuable to me. I have no idea how much it would be worth right now. But I mean, if you look at when you're in the lab, you'll see that your beakers look absolutely nothing like this. So because of all the experiments that we do with chemistry, we have a pretty good idea that that is the way atoms look. That is their structure. Bear with me. I just saw another name that I'm making a roll to submit for the registrar's office. So I just need to write down one more name. Oh, let me go back to share my screen. Oh, that's great. So, So elements are negative, electrons are negatively charged, protons are positively charged, and neutrons are neutral in their charge. Electrons are negative, protons are positive, neutrons are neutral. So what is the overall charge on the nucleus? Somebody tell me what you think. Bless you.
Neutral.
That's what I was gonna say.
Let me give it to you one more time. Protons and neutrons are in the nucleus. And neutrons have a neutral charge. Protons have a positive charge. What's the overall charge on the nucleus?
Positive.
You're right, it's positive. What's the overall charge on the electrons?
Negative.
Negative. So when you think about opposite charges, do they attract or repel?
Opposites attract.
Opposites attract, correct. So the positive charge of the nucleus and the negative charge of the electrons are what keep the electrons orbiting around the nucleus. If you think about it that way, think of it like it has a gravitational pull. Now, my question for you is, if the electrons are orbiting the nucleus and the nucleus is positive and the electrons are negative, and that's why they stay orbiting, why aren't they falling into the nucleus? I mean, if there's a pull, why are they not just colliding into the nucleus? There's an energy there that's keeping them. They're attracted, but there's an energy there that's keeping them from collapsing. Keep that in mind for a few minutes here. One other thing is, we know that these electrons, they move in these orbits and they circulate. However, electrons are so small and so little in comparison to the nucleus that their location and their movement, their location and their mass are almost negligible. They're so little that at any given moment, we cannot pinpoint exactly where one is. On average, we know that they're within a certain orbit and within a certain shell. However, where one is at any given moment, we cannot say. On average, they're within these orbits. What that means is that even though we write an atom out like this, because we have to be able to draw electrons, we may not be able to pinpoint them in space, but we have to be able to draw them. We know that it may look, we may draw it like this, but in all actuality, the nucleus looks like this, where the electrons are actually more in a cloud, where their most average path is going to be one of the orbits. But that one electron at any given moment, it may be right here. On average, it's going to be at this more darker spot. But at any given moment, it could be out here. At any given moment, it could be closer to the nucleus. But on average, this is where it tends to be. keep that in mind, that that's the way it actually is, but we write it out like this because we have to be able to draw electrons. We have to be able to map where they are a little bit in order to understand chemistry. Any questions? So atoms are the smallest particles of an element that still exhibit the chemical properties of that specific element. Remember that if I tell you this is 100% carbon, all of the atoms of that ball that I give you are all the same atom structure. Have all of the atoms of that and that mass that I give you that I say this is 100% carbon. All of that is one type of atom. And the structure of all of those atoms are the same. If you remember, we talked a lot about structure and function. All of the atoms of carbon have the same similar structure. All of the atoms of iron have the same basic structure. And their structure is going to determine their function, because we know that structure is function. Structure dictates function. So with these planetary models of atoms, we often they're also called Bohr models of atoms. So we draw them so that we have a nucleus in the center, and we have electrons in orbits or shells that circulate the nucleus. The hydrogen atom has one electron and one proton. The carbon atom has 6 electrons, has 2 in the first shell and 4 in the next. The first shell of any atom can contain 2 electrons. All other shells can contain up to 8 electrons. So the first shell contains 2. All other shells have 8. The most outer shell is the valence shell. If I give you an atom and I say this particular atom has 22 electrons, can you tell me how many electron shells it has?
Three.
Why do you say 3?
Well, because the first one has 1.
No, actually the first one has 2.
Oh, okay. So the first one would have 2. The second one would have 8. So that's 10. The next one would have, so it would be 3.
Or would it be 4? So
I'm
first
doing the
one
math
has,
in my head.
I understand. No, I understand. The first one has 2. We said it had 22, right?
Right.
Okay.
Right.
First one has 2. Second one has 8.
It's 10,
The next one has 8.
18.
And so there's 3. The fourth one is going to have 4.
Mhm.
Does that
Okay.
sound about right?
Yeah.
Okay. No, and I understand, and I also am well aware that it's early and it's a Friday morning. Let me tell you, I feel the same way.
It's been a long week.
I understand more than I can tell you. This is my last class of the week, and I always think, Mary, can you just make it until 11 on Friday? So life is an adventure. So with this in mind, that is the way all atoms work. 2 in the first shell, 8 in all of the next. If an atom, and this is kind of skipping ahead, but if an atom has less than 8 electrons in their valence shell, the valence shell is its most outer shell, it will react with other things to get 8 and complete an 8 in its outer shell. It wants to have 8 in the outer shell. It may give up some electrons in order to have 8 in its outer shell. So let me give you an example of that. This, let's see here. Actually, let me wait on that one just for a second here. But keep that in mind. It wants 8 in its outer shell. It honestly doesn't care very much whether it gets those electrons and fills its outer shell with 8, or it gives up electrons so that its next outer shell has only 8. So it can give them up, it can share them, but it wants to have 8. That's the key here. If it only has 1 in its outer shell, it may give it up to another atom so that it doesn't deal with a shell that's incomplete. That's key here. So the periodic table, and no, you're not ever going to be asked to memorize the periodic table. And I know you're all being very grateful for that at this moment.
Yeah.
I was a chemist as an undergraduate. I can say that I was never asked in my life to memorize the periodic table. I don't have it memorized at this moment. A lot of the atoms, I can give you a general idea of which ones that I deal with most. I have a general idea where they are. I have a general idea what their symbols are. I may have a general idea of more things about them, but I do not have this memorized. The most important thing about the periodic table is you need to know how to use it. You need to be able to look at one and figure out what you need. And by the time that you're done with your nursing or your healthcare or your biology degree or your chemistry degree, you will have looked at this several times and you'll start to get a grasp of where certain elements are that you use a lot. Hydrogen right here, carbon right here, oxygen right here, iron right here, calcium right here, sodium right here, potassium right here. You'll get a general idea, but in this class, we're going to talk basically about how this is organized. So elements are arranged on the periodic table according to their atomic structures, which results in their different chemical properties. So based on their atomic structures, how their atoms are organized, remember the electron shells, how their atoms are organized, that is how they are placed on this periodic table. I didn't mean to go down that far. Give me 1 second. So the vertical columns on a periodic table are called groups. All elements of a certain group share similar reactive characteristics. They form the same types of chemical bonds. All groups, vertical groups, share the similar chemical characteristics, have the same kind of bonds. Horizontal rows, all of these elements have the same number of electron shells. And their atomic numbers, which we'll talk about next, increase by 1 as you move from left to right. So here's the atomic number of lithium right here, 3. Beryllium is 4. Barium is 5. Carbon is 6. Nitrogen is 7. Oxygen is 8. Fluorine is 9. And neon is 10. The atomic number is defined by the number of protons within an atom. So within hydrogen, it has 1 proton. So its atomic number is 1. In stable atoms, meaning that they have a overall neutral charge, number of protons equals the number of electrons. I think I need to not put stable atoms. I think I'm going to change this word and put neutral atoms. In neutral atoms, the number of protons equals the number of electrons. Nevertheless, the number of electrons is going to determine the chemical behavior of an atom. If you think back, you remember what I was talking about with that two in the first shell, 8 in the next shell, and then an atom will work to get 8 in whatever valence shell that it has. Do you remember me saying that? I like that I see so many faces here. Mm-hmm. You remember that I said that before? So with that in mind, the number of, if I have less than 8 in that outer shell, as an atom, I'm going to react to either give them up or get more until I have 8. The mass number is the sum of the number of protons and neutrons. Isotopes, however, are atoms with the same number of protons and electrons, but they contain different numbers of neutrons. For example, hydrogen has 2 isotopes. deuterium, remember how I said that hydrogen only has one proton? It doesn't have a neutron. However, the two isotopes of hydrogen, deuterium has one neutron and tritium has 3. No, I'm sorry. Oh, good grief, Mary. Be able to count. One isotopes. Hydrogen has 1 neutron. Tritium has 2 neutrons. The regular hydrogen atom has 0 neutrons. The atomic weight is the average weight of the mass numbers, meaning the sum of the protons and neutrons, if you consider that each proton and neutron is equal to 1 with its regards to its mass. The average weight for any given chemical element is its atomic weight. And that average weight is all the isotopes of a given element. So hydrogen atom, if you look, this is its atomic weight, 1.08008, which means that on average, hydrogen exists like this. However, on every once in a while, we get deuterium and we get tritium. So that on average, when we calculate all of the masses of a lot of different isotopes of hydrogen, this is what we get. So the major thing that varies isotopes from our normal atoms is that they can, the same atom of a given chemical element where the number of protons and the number of electrons are the same, but the number of neutrons varies. Now, the element lithium has 3 protons and 4 neutrons in its nucleus. So what's its mass number?
7.
You're right, it's 7. Good job. An atom with a mass number of 18 that contains 10 neutrons would have an atomic number of what?
8.
Why do you say that?
Oh no.
No, you know. You can't
'cause
randomly guess that.
No, the atomic number is the number of protons. So if it has 10 neutrons, that would leave it with 8 protons.
Good job. Yes.
Oh, yay.
I was like, no, there's no way that you randomly guessed that perfectly.
No, I didn't.
that was funny though. So isotopes of any given chemical element, within their atoms, they have the same number of protons, they have the same number of electrons, but they have differing numbers of neutrons.
Okay, let's see.
some isotopes, or actually, let's not even say some isotopes, let's say all isotopes. Some are more stable than others. But isotopes are unstable, and they will lose nuclear particles until they become stable. When we think about nuclear particles with electrons, neutrons, and protons, they will continue to lose nuclear particles until they become stable. Meaning that their number of protons equals their number of excuse me, Leo, you can't be up there. I'm sorry, guys, just say. My cat, you are a stinker. But it's not like he didn't know that. He's my 14-year-old special needs cat, and so he's kind of a stinker, but I've had him since he was about 8 weeks old, so he knows he's mine.
I think he took a picture on your screen.
Oh, did he? Oh, that's great. Okay. Oh, yeah, he did. Oh, shoot. Okay, that's great. You know you're a pill, right?
Isotopes.
He knows he's a pill, but he also knows that he's my pill, so we're good.
Yeah.
So isotopes, unstable, they will lose nuclear particles until they become stable. Some isotopes, heavier isotopes, are very unstable. And their atoms will decompose spontaneously into more stable atoms. So if you think this is something that's decaying, so it's just constantly decomposing until it becomes more stable. Think of something decaying in your fridge. This is the same thing here. It's the same thing. So it's just going to continue to break down until it becomes more stable. This process of atomic decay is called radioactivity. This decay involves the emission of alpha, beta, and gamma rays from the atomic nucleus. These elements can transform into other elements. So we have three different types of decay that can come off radioisotopes. We have alpha emission rays, where the decay is in the form of a helium nucleus, which includes 2 protons and 2 neutrons. So one isotope will decay, and when it decays, it will give off a helium nucleus every time. And this is defined as an alpha ray. Another type of isotope will decay, and every time it decays, it will give off an electron in the form of a beta ray. Another type of isotope will decay in the form of and give off photons or light rays. Photon is a light wavelength, which we define as being gamma rays. As they decay, they are being transformed into other elements. Alpha emission, remember that was the helium atom, is the least penetrating, meaning it's the least damaging. Nevertheless, inhaled alpha particles that come from radon causes lung cancer second only to smoking.
You said that as these as they decay, they are being transformed into what other
more stable elements. And that they'll continue to do that until they stop giving off radiation.
Okay, thank you.
You're welcome. I like that you guys are a very open class. You're very verbal, and I really like it. It's easier for me to teach online classes when students are talking with me, because then I don't feel like you're in your own little world and I'm in my own little world. Gamma emission has the greatest penetrating power. Remember, these were the electrons. No, wait, these are the photons. This is what's used to destroy localized cancers. Ionizing radiation, or beta rays, knock electrons out of atoms, and these electrons then go on to destroy other things. Now, my question for you is, how do these electrons go on to destroy other things? And now let me put it this way. If you remember, we talked about how electrons are involved in, we fill that first electron shell of an atom with 2, fill the second one with 8, fill the second one with 8. If we give any atom an extra electron that it didn't have before, it's going to change how that atom reacts with other things. So when you get ionizing radiation that is randomly knocking electrons out of different atoms, and then those electrons then go off and conglomerate onto other atoms randomly, you're going to cause chaos with regards to how atoms function. That's how they go off and destroy other things. Is that clear? Okay. Mm-hmm. Good. Radioisotopes will gradually lose their radioactive behavior. The time required for one radioisotope to lose 1/2 of its activity and become a more stable atom is its physical half-life.
Okay.
Half-lives can vary between hours to thousands of years. So if I give you a bunch of radioactive cobalt-60, and we say, here we have 10 grams here, and 60, actually, wait. And one half-life in 5.27 years, the 10 grams that we started with, we will only have 5 grams in 5.27 years. We'll only have 5 grams that are actually radioactive. That's the half-life. The biological half-life is how long will a radioisotope let's see, bear with me. How long will a radioisotope, at what point is that radioisotope only giving off half of its radiation? That's the biological half-life. Questions? I don't know how to unclick changes photo, and I'm sorry that my cat decided it was a good idea to take a photo at that moment, because I don't know how to change it. We often use radioisotopes as tools for biological research and medicine. If you remember, very first day we talked about PET scans, positron electron tomography scans, where we insert a radioisotope labeled metabolite like glucose and look to see where the most emission is coming off in the body, because that's an indicator of how actively that given metabolite like glucose is being broken down in a certain area. That's where radioisotopes have a lot of uses in medicine and research, because they share the same chemistry as their normal stable atoms. We can use them to localize and eliminate damaged or cancerous tissues, such as in the thyroid. This is an example of a scan looking in the thyroid gland. So Graves' disease causes an enlargement of the thyroid gland called hyperthyroidism. We can insert, and normally what they do is they add label iodine. They radioactively label iodine and watch its metabolism. In a normal thyroid, you see a mild amount of emission. However, in Graves' disease, where we have hyperthyroidism, the amount of emission being given off becomes much bigger, much greater. You guys, let's go through this little set of questions and then let's take 10 minutes. For any particular element, the number of blank can vary, and therefore the mass number of an element can vary.
For any particular element, the number of blank can vary, and therefore the mass number of the element vary.
What would cause the mass number to vary?
Electrons?
We'll go back and look at what the definition of a mass number is.
Sum of the number of protons and neutrons.
Does the number of protons usually vary?
I was going to say D, neutrons.
Why do you say neutrons?
Just because
Because the number of protons typically doesn't vary, right, Jade?
yeah,
Yeah.
they
Okay.
come and go. I was gonna say that, but
You're right. You're right.
okay.
Okay, let's take 10 minutes right here. Just because I know if I get tired of looking at my screen, you probably get tired too. Let's take 10 minutes. So let's come back at 10 o'clock.
All righty. Thank you.
You're welcome. I'm going to get up and get a glass of water. Wait. Wait. Sweet girl. Hi. Jade, are you there?
Yes, I am.
What question were you asking me about? Do you remember? Online.
Yeah, so for some reason, like I seen, even when she had took me, I forget who it was that had showed us how to get to the information for the lab. For some reason, what I had took is what had popped up in the 8:30. I do not see, like, for instance, like, I know whatever it was that I had completed, it had took a pretty long time to complete. And when I go back, there's like nothing else there for me to submit or to click on to be able to do, like, for instance, like the practice quiz, and then where it actually like
Can
says
you,
quiz.
when can you know what? All right. I'm after class. I'm gonna ask you to share your screen with me.
Okay.
And let's see what it is.
Okay. All right. Sounds good. Thank you.
You're welcome, of course. Oh, I should stop sharing, Mary. Okay. Okay. So coming back with this idea of atoms, and they can give up or add to their number of electrons to get 8 electrons in their most outer valence shell. A molecule is defined as 2 or more atoms that are held together by chemical bonds. And a compound is 2 or more atoms of different elements that are bound together. So all compounds are molecules. All compounds are molecules. But are all molecules compounds? All right, Jade, you're quick. Why is it not?
That I can't recall. I just know I took a science class before, and I just remember that they're different.
Okay.
I don't know exactly why. I just recall that they are different though.
Okay. So let me give you the definition one more time. A molecule is two or more atoms held together by chemical bonds. Compound is two or more atoms of different elements. A molecule that contains only one type of atom, one element's atoms, is not going to be a compound. I like that you guys I can see your faces, because when you understand, you nod, and I really appreciate it. Each molecule can be represented by a molecular formula that identifies the numbers of each atom of a given element within that molecule. So a molecule is the smallest particle of a compound. Remember, a compound is one or more different atoms of a given element that still exhibit the same characteristics of the compound. So remember, a compound has two or more different types of atoms of different elements found. A molecule is the smallest part of a compound that still has the characteristics of that compound. The molecular weight is the sum of the atomic weights of each atom within a molecule. So we're adding the atomic weights of each atom within a molecule. And that is what gives us the molecular weight.
So would that be like how hydrogen was like 1 point something plus, say, whatever the next?
Yep.
Okay.
So if we think like Becky was saying, hydrogen has an atomic weight of 1. Hydrogen gas has that's got 2 hydrogen atoms bound to one another, has a molecular weight of 2. Isomers are molecules with the same molecular formulas, but the atoms are structurally arranged differently. So when you think the molecular formulas is the number of each of the different types of atoms within a molecule. But it doesn't describe how the atoms are individually bound to within that molecule. So some isomers have the same molecular formula, but the atoms of the different chemical elements are arranged differently. Ethanol, which is the alcohol that we have in our alcoholic beverages, has a structural formula that's showing how carbon is bound to the hydrogen, the oxygen and the hydrogen. Has a structural condensed formula of this. Has a molecular formula of this. Ethyl ether, which is a gas. And I think if I remember right, I'm pretty sure this is what they used to use to put people under until they realized how carcinogenic it was. Ethyl ether has a structural formula of this, has a condensed structural formula of this, but its molecular formula is the same of that of ethanol, because they each have 2 carbons in them, 6 hydrogens and 1 oxygen. So shoot, just like. Bear with me. The chemical and physiological effects and properties of 2 isomers can be very different. Their reactivity with other things can be very different. I would, rather than say, I'm going to change this chemical and physiological effects, I'm going to say properties or characteristics can be very different. I'm sorry, give me 1 second. This laptop is fairly new to me and it's very touchy. Give me 1 second here. So an example of isomers, L amino acids are one isotope of a given amino acid. D amino acids are another type of isomer of an amino acid. D amino acids are not incorporated into proteins. We'll talk about how amino acids are the building blocks of proteins. However, D isomers of amino acids cannot be used in proteins. They're just structurally, they do not function well. So different isomers can have different effects. When atoms combine with other atoms, they're held together by chemical bonds. This bond is an energy relationship between the electrons of the reacting atoms. The likelihood that an atom will form a chemical bond depends on the number of electrons in its valence shell. What is the valence shell again? Do you remember?
It's the outer neutron.
Outermost shell.
Yeah, the outermost electron shell.
Yeah.
So the likelihood that an atom will form an chemical bond depends on the number of electrons in its outer shell. The atom is most stable when its valence shell is full, meaning it has 8 electrons or 2. 2 in the first one. I can't believe I just did that. 2 in the first one. Two in the first one, and 8 in all the next ones. This fact that 2 are required in the first shell, 8 are required in all other shells, is what we call the octet rule. If you think about what an octagon is, octagon meaning a shape that has 8 sides. Octet rule says that the most outer shell outside of the first shell will be most stable when it has 8 electrons. So an atom will continue to react with other atoms until it has 8 electrons in its most outer shell. It can give up electrons, it can take on more electrons, but it will continue until its most outer shell has 8.
No matter what, it's going to keep going until it gets 8.
Yes, it will react in some way. The noble gases, which are, well, I wish I should put a part of this on our on the PowerPoint here. The noble gases, which are the very far right column on the periodic table. The noble gases, they don't react with anything because their valence shell of their atoms are completely full. Go ahead.
Yeah, I got it.
And now I don't even have a camera at all. You guys can't see me at all. Really? I'm not sure why you don't see me. That wasn't what I wanted. Oh, that wasn't what I wanted either. Bear with me just for a second here. I'm sorry you can't see me. I want you to be able to see me, and I don't know what happened that made it so you all of a sudden just don't see me at all. Anybody know how to help me fix this?
Can you still see yourself in the box?
No. So I know that you probably don't see me either.
No, if you click on the box, does it allow you to start video or something?
No.
I know, like on our end, if we click on our box, we can, in the corner, it'll say start video, and that's how we show our faces.
Or you can switch camera. Like, I don't know if you can press where it says switch camera and see if it'll go on again.
You're on mute.
Oh, we have your picture, but no sound.
Oh, that's cool.
Now do you hear me?
Yeah, there you are.
Okay.
Yeah.
I apologize. Give me 1 second. Let me get back. Okay. So with this in mind, an electron shell within an atom represents a different energy level. Remember, I asked the comment, I asked what prevents the electrons if they're orbiting because they're attracted to the positive charge in the nucleus. What prevents them from colliding into the nucleus? There is an energy level that keeps them apart. There's a certain energy that's keeping them apart. If you think we've all played with magnets at some point, and they have an opposite and a positive charge. And when you put them right next to one another, you have to hold them, you kind of have to hold them apart because they're so attracted to one another. That's the energy that you're using. You're physically imposing an energy on them to keep them apart. That's the same thing that's occurring in the electron shells versus the nucleus. Electrons that are farthest from the nucleus or in the valence shell, they have the highest potential energy. They have the highest energy because they work to overcome their attraction to the nucleus. They're most likely to interact chemically with other atoms. Give me 1 second here. Okay, so you can't see them really well, but I have two little magnets here. Stop sharing for 1 second. I have two little magnets right here. I can put them, actually, these little guys are going to repel one another. Thanks, guys. You're not playing very well here. But there is a certain amount of energy, if they're moving towards one another, there's a certain amount of energy that they're going to repel one another and they're going to try to get close. However, at a certain level, there's a certain, I have to work to keep a certain distance. I have to work to keep them apart. Afterwards, there's that pull becomes weaker, right? The further once I overcome that gap, that energy barrier where it's the strongest, the further they get away from one another, the more likely they are to be lost. They're no longer going to be attracted to one another. Same thing with electrons. and the protons. So electrons that are the furthest away from the nucleus are more likely to react with other electrons from other atoms. They're more likely to react with the electrons of other atoms. So remember with this in mind, so electrons that are the furthest away from the nucleus are more likely to react with the electrons of other atoms or react with other atoms. And bear with me here. And simultaneously, we know that all atoms want to have their shells filled. Remember that octet rule. They want to have two in the first and 8 in all the others. I have a nucleus here, has an overall positive charge, or it just has a positive charge. Have an orbit, a shell here, have a shell here. Really bad looking shell, but it's a shell here.
Egg.
Another shell here. This has 2. This has 8. This has more. The 8. 1, 2, 3, 4, 5. One more. And this has 2 out here. Another one, another different atom. It's 2 here. Has 7 out here. So this atom here has 2 in its most outer shell. In order to become stable and not react with other things, it either has to take on 6 more electrons or give up 2.
This one?
The one, yep, the one on the left.
Oh, that.
What's easiest for it to do?
Give up 2.
It's going to give up 2. You know, even though, you know, you want to think more is better. Atoms don't think like that. They really just want to be the most stable. They don't think at all, but we're going to pretend that they do. They just do it. So 2, and this one over here has 7. Is it easier to give up 7 or take on 1?
Take on 1.
It takes on 1. With that in mind, an anion is a neutral atom that gains electrons. Oh, wait, I'm sorry. Do you see my screen? Do you see the PowerPoint?
No, we see your
Oh,
drawing.
shoot. I knew that. Okay. Knew that. You see it now?
Yep.
Okay. So a neutral atom gains electrons. At that point, it has more electrons than it does protons because the proton number hasn't changed here. So the number of electrons is greater than the number of protons. So that atom now has an overall negative charge. A cation that loses an atom that loses electrons is now going to have a net positive charge. Because now its proton number is greater than the electron number. We call when a neutral atom takes on more or gives up electrons, it's now got a charge on it. We call these ions.
Can you repeat that?
When an atom gives up or takes on more electrons so that the number of electrons is no longer equal to the number of protons, it now has a charge on it. An atom that has more electrons than protons has a negative charge, so it's called an anion. An atom that has more protons than electrons is called a cation because it has an overall positive charge. And opposite charges are attracted to each other. And so ions with opposite charges are attracted to each other. So sodium has 1 electron in its outer shell. It's easier to give up 1 than take on 7. So it gives it up. Chlorine has 7 in its outer shell. Easier to take on 1 than give up 7. So sodium after this exchange of electrons, sodium now has an overall positive charge. Chlorine has an overall negative charge. And they bind together based on their opposite charges attracting. We'll talk about it here in a second, but that's an ionic bond, where they're interacting based on their opposite charges because of the exchange of electrons that they've already done. Any questions about this? The reactive properties or chemical behavior of an atom mostly depend on the number of what?
Electrons.
The number of electrons in each shell of the atom, or the number of electrons in the outer shell, or the filled electron shells?
The outer shell.
It's the outer shell. What is the other name for the outer shell?
The valence.
The valence shell, correct.
Yeah.
And you know what? And let me tell you, I will try really hard not to correct you a lot of times on pronunciation unless I really know that you're not right. Because depending on who you talk to and where you learned it the first time, everyone sometimes pronounces things a little differently. What, Mom?
Potato,
Potato, potato is what she says. And she's
Mhm.
right. Tomato, tomato, same thing. When atoms gain electrons, what happens?
It gets a negative charge.
So what is number D? So the atoms become negatively charged. Inorganic compounds or salts. Bear with me. Ionic compounds containing cations other than hydrogen ions and anions other than hydroxide are called salts. So ionic compounds that do not contain hydrogen ions or hydroxide anions are salts. These ionic compounds, when dissolved in water, will dissociate into ions. The ions are electrolytes because they can conduct an electrical current in a solution. Things with a charge will conduct a charge. When you think of an electrical current, what you're looking at is hydrogen ions, excuse me, not hydrogen ions, electrons being moved from one structure to the next. So if you think electrical current, electrons. So ions are electrolytes that can conduct an electrical current in a solution. The most common salts found in the body are sodium chloride, calcium carbonate, and potassium chloride. I told you that you don't have to memorize the periodic table, but you'll see that I often use the chemical element names rather than write them out.
Mhm.
And I'm doing that to get you used to thinking of them that way. Other common ions are iron with a +2 charge, iron with a +3 charge, copper with a +2 charge, zinc with a +1 charge, iodine with a +1 charge, and magnesium with a +2 charge. In each of these cases for these ions, how did iron get a +2 charge?
It lost some electrons.
How many did it lose?
2.
You're right. Yes. So if you're given an ion on an exam, you can tell me how many electrons it gained or how many it lost.
So like, for example, the zinc that's positive, that gained 1.
Did it gain 1 or did it lose 1?
Well, it just has a plus, so I want to say gained one.
Gained what?
One electron.
But what is the charge on an electron?
Oh, yeah. They are positive, so wait. An electron is a negative charge.
So would a zinc with a positive one positive charge, is it going to lose or gain an electron to get that charge?
No idea.
You do too. You do too. You do too. Becky, you're really good at saying this, but I know you know. If the number of protons equals the number of electrons, then the overall charge on something is 0.
So then it gained one.
No, wait. Are you talking about the zinc?
Yeah.
Did it gain a proton? They remember the protons are in the nucleus.
Okay.
Are they likely to be lost or gained? Probably not.
Okay.
It's gonna lose or gain an electron every time. The protons don't really move for the I don't think they're gonna move very much.
Right.
But the electrons are the ones that can be moving around. So to get a overall positive charge, it has to give up an electron.
Okay.
Does that make sense?
It does, to an extent. Like I see where the copper is +2, so you know that gained 2.
It didn't gain 2.
It lost.
It lost 2
It lost 2 what?
electrons.
Correct.
Right. Okay.
This just takes practice.
Yeah.
It takes, practice wrapping your head around it. By far, this is probably one of the more, I think this semester is going to be one of the more difficult chapters to wrap your head around.
Chapter?
This chapter 2, one of the more difficult chapters for wrapping your head around. Electrolytes are substances that ionize in water. So they become ions in water and form solutions that are capable of conducting an electrical current because they can take on and give up electrons. Electrolytes are crucial in anatomy and physiology, and we use them to detect electrical activity of muscles, heart, and brain with electrodes on the skin because electrolytes in body fluids can conduct currents. And from these organs to the skin.
What did you say it gives up again?
They give up and take on electrons from other, so it's like a chain of one atom giving up an electron to another atom. And that atom then can give up those electrons to another atom. And it's a chain. That's how a current is produced. And so all ions have the ability to do this. Because they have a positive or negative charge, they will take on other things. Things that have a charge are going to react with other things. Electrolyte balance is one of the most important considerations in patient care. Imbalances lead to coma and cardiac arrest. When we talk about the nervous system, which is coming, we will talk a lot about how different ions are involved in conducting nerve signals. So one of the most important electrolytes and salts involved in the body are listed here. Free radicals are highly unstable chemical properties with an odd number of electrons. If you think remember the first electron shell takes on 2, the second one takes on 8, the next one takes on 8, the next one takes on 8, the next one takes on 8. Highly reactive chemical properties with an odd number of electrons, so meaning 1 or 7 or 5, meaning they never have they're going to struggle to maintain a full shell, are produced in normal metabolic reactions or by radiation or chemicals. These free radicals are short-lived. Are short-lived because they easily combine with other biomolecules, because they're always trying to lose or gain something. Not something. They're always trying to lose or gain an electron. So they're constantly combining with other molecules and converting them into free radicals that then go on to convert other things to free radicals. When you're constantly dealing with an odd number of electrons, you are always wanting to react with other things. And when you react with other things, you force them to become free radicals too. This is what we call oxidation. A major part of why people age and bodies age is based on the fact that we're constantly accumulating free radicals. That's why they like us to take antioxidants. Free radicals lead to destruction of other molecules in the body. Oxidative stress is a state that occurs when there's an excess of free radicals. It can cause cells to lose their structure. Remember, if we lose structure, we lose function. So this leads to diseases like cancer, diabetes, aging, atherosclerosis, and at least 45 others. My little dog that you saw bouncing around a minute ago, she's developing cataracts. And I need to look it up. I think I'm going to try to look it up this weekend, but I'm pretty sure that's a sign of oxidative stress. Antioxidants like zinc, if you remember that positive charge on zinc, vitamin C, vitamin E, beta carotene inactivate free radicals by taking on free electrons. antioxidants donate electrons to free radicals, stabilizing them.
Said they donate?
They donate. So at that point, the free radical is neutralized.
Okay, so antioxidants donate electrons.
Yeah. And they donate them to free radicals that have an odd pair of electrons, allowing that free radical to now have a complete shell.
So then is it a free radical at that point?
Not anymore, it's neutralized.
Okay, that's what I was going to say.
Good question. So this is why we're constantly being asked to have antioxidants in our diet, as Catherine Roberto or Roberts, I can't remember exactly. Catherine, I know you're there. Which one it is, but the one who is talking about nutrition. One of the reasons we're constantly being asked, or it's being promoted to take on more antioxidants. Superoxide dismutase is an enzyme that is able to break down potentially harmful oxygen molecules in cells. It is a very important antioxidant defense. Paisley, really? Okay, stay there. Very important antioxidant defense against oxidative stress in the body. So its job is to break down the free radicals of oxygen.
Can you go back a second?
Yeah, I was going to.
That helps.
So oxygen in a regular is constantly being developed into a free radical in the body by regular metabolic activities, because you know we use oxygen on a pretty regular basis. When it reacts, it a lot of times will form what's called superoxide. Superoxide can be neutralized and broken down into hydrogen peroxide. That hydrogen peroxide is then further broken down by peroxidase catalase into water. Enzymes are proteins that catalyze reactions in the body. Shifting gears a little bit here. An ionic bond is a bond that's formed by the transfer of one or more electrons from one atom to another that produces ions that are then attracted to each other, thus creating a salt. So we've talked about this a little bit. We're going to do some repetition here. I think it's a good idea because it helps us all. We're developing a puzzle in our head of different things that we're learning. Now, how do we put them all into a pattern and a process? So a bond being formed by the transfer of one or more electrons from one atom to another produces ions that are then attracted to each other, thus creating salts. I'm so sorry. Give me one. I don't know why this is so funny. Ionic bonds are most commonly formed between atoms that have one or two valence electrons, because they're the ones who are most likely to give them up, and atoms with 6 or 7 valence electrons in order to fulfill that octet rule. So they're most commonly formed because of the likelihood of being able to fulfill the octet rule. One atom that has 1 or 2 electrons in its most outer shell is most likely to give them up to an atom that has 6 or 7 valence electrons. In the dry solid state, ionic compounds are salts which do not exist as individual molecules, but they exist as crystals that are large arrays of anions and cations. So when an atom gives up an electron or takes on an electron, it then develops a charge where it's attracted to another atom that has given up or taken on an electron. That's an ionic bond. Another bond is covalent bonds. Covalent bonds are the most common and the strongest chemical bonds in the body. This is where they share them. Rather than give up completely an electron or take one on completely, they share them. This is the most common and strongest chemical bond. These ions are formed by electrons being shared, where the electrons occupy a single orbital.
Share by, oh,
This is a little mixed up, and I'm sorry, they kind of squished this slide together. Oxygen here, methane here, and water here. If you download this, it won't look smushed like this. We can have molecules where there are single covalent bonds between atoms, where one pair of electrons are being shared. One single pair. So 2 electrons are being shared between the 2 hydrogen atoms in this case. Double covalent bonds occur when 2 pairs of electrons, so 4 electrons are being shared. triple covalent bonds occur when 3 pairs of electrons are being shared. In an oxygen molecule, and here's your oxygen molecule right here, or right here, here's another oxygen molecule. How many electrons in total are being shared between the 2 hydrogen atoms?
E.
4.
You're right, 4. So there's 2 covalent bonds. Each bond has 2 shared electrons. So there's 4 being shared. When the electrons are being shared equally around each nucleus of the atom they're being shared, with which they're being shared, we say that they're being shared equally. This is a non-polar covalent bond. Let me, a way to remember this. If you, and no offense to people who are bipolar. I have friends, I have family members who are bipolar. But what does it mean when we say that someone is bipolar? What does it mean when we say that someone is bipolar? It means that they have two opposite poles when it comes to their personality. They often have two opposite sides, and it's hard to bring them together, and it's hard to keep them stable. So a non-polar, meaning they're equally shared and there's no 2 opposite sides or 2 opposite areas. When atoms don't share electrons equally, we get polar covalent bonds. So there's an unequal sharing of electrons. The nucleus of one atom attracts the shared electrons more than the nucleus of the other atom, which is sharing the electrons. So we have non-polar covalent bonds where the bonding electrons are shared equally between the 2 atoms, and there's no charges on either atom because of the equal sharing. We have polar covalent bonds. Oh, I'm so sorry. Give me a. We have polar covalent bonds where the electrons are being shared unequally. And the result is that there's partial charges on the atoms. If you think about the fact that this chlorine atom is holding on to the shared electrons more than the hydrogen atom is, the result is that this side of the molecule is going to have a more negative charge than this side. And this side, because the proton here is more exposed, it's going to have a partial positive charge. Ionic bond is that complete transfer with full charges on the resulting ions. So on polar covalent bonds, there's going to be a partial charge on the two atoms. Because one of them is holding on to the electrons more than the other. Any questions? Small atoms with usually 6 or 7 valence electrons are electron hungry. Therefore, they attract electrons very strongly. These atoms are the electronegative ones. So atoms that are more hungry, electron hungry than other atoms are called electronegative atoms. Most atoms with 1 or 2 valence electrons only have a very low electron attracting ability and are often described as being electropositive. And they tend to lose their valence electrons because they don't attract them as much to more electronegative atoms. So atoms that are more electronegative are hold their electrons closer, and they hold other atoms' electrons closer. Atoms with 1 or 2 valence shell electrons don't hold on to them as tightly, and they're more likely to give them up to a more electronegative atom. I'm going to go for just 2 more minutes here. This electronegativity depends on an atom's atomic number and the distance of the valence electrons from the atom's nucleus. So the higher the atomic number, the more positive the charge. Remember, because the atomic number is the number of protons, the more positive charge that nucleus has, the more likely it is to pull on its electrons that are negatively charged.
Can you say that again?
The more protons an atom has, the more likely it is to pull on its electrons. More protons it has, because the more positive charges it has in its nucleus, the more it's likely to pull on its electrons. Also, because we know, like I showed with the magnets before, that didn't work very well, but the theory is right. So positive and negative charges attract one another. But after a certain distance, once the positive and negative charges are a certain distance away from one another, that attractive force goes away, or it diminishes. So electronegativity depends on the atomic number and the distance of the valence electrons from the atom's nucleus. So how many electrons are there? The ionization energy is the energy that's required to remove the most loosely bound electron. So the most farthest one out. So electronegativity depends on the atomic number, the distance of the valence electrons from the atom, and the ionization energy, the energy required to remove the most loosely bound atom. So on the periodic table, atoms' electronegativity goes up as we move to the right. It goes up as we move to the top. That's the general trend. So fluorine here, these are the noble gases. Remember, they don't react with anything. However, these right here, iodine, fluorine, chlorine, selenium, sulfur, oxygen, nitrogen, are highly electronegative. Hydrogen is the least electronegative. Let me shift down a little more. And I think this is a really, really good place to stop. Really quick, I know it's the end of class. Are there any questions?
No.
Okay.
Oh yeah, real quick.
Yeah.
You said we can do the practice quiz as many times as we like.
Yes. Just keep doing it. Your highest score will be the one recorded.
Okay.
Let's see here. Bear with me just for a second. I have to. If you don't have any questions, I will see you next week.
I have one more.
Okay.
So the study for each chapter that we have to fill out, are they going to be the questions on the test?
I'm sorry, say it one more time.
Study sheets that we have for each chapter,
they will be that is the material that's going to be covered on the exam.
Okay.
It probably won't be exactly like that. Well, I'll tell you, a lot of your questions are going to come from your chapter practices and the chapter quiz. Some of them are the same questions. Some of them are not. You're going to be given on the quiz and on the practices, you're given a random pool of some questions I've selected.
Okay.
The practice is not timed. The chapter quiz and the exams are.
Okay.
Okay.
Sounds good.
Jade, one moment, all right? I need to, before we address what's going on with your stuff, give me 1 second because I need to make a note of which which slide we ended on. So give me 1 second here.
Bye.
Bye. We'll see you later.
All right, have a good weekend.
You too.
Thanks.
Be patient with me for 1 second. If I don't do this now, I don't remember, and that's and oh, let's do it differently. So 50. All right. Okay. So Jade, I'm going to stop sharing my screen.
Okay.
And I want you to show your screen. I think I stopped, so you should be able to do it now.
Okay. You can see my screen?
Yep, I can.
So like when I go into here, for instance, and let me get to it.
Sorry, I stayed because I was trying to see if I'm having the same problems.
No, you're
like
okay.
why I'm still here.
So this is where I'm lost. Like, okay, for some reason now it's coming up. I'm not getting what I was, but okay, so like over here, for instance, I wasn't seeing this. Now, what confuses me though is I don't know which one I took, because before when I would log into here, there was only one thing here. And
Really?
I think, yeah, and I think it was this one. So like, for instance, when I come up here to the top, it'll tell me, this one right here. And I know it has
nobody. No. Go. Sorry.
No, you're fine. I just don't know what I completed and what still needs to be completed, because when I was first logging in, like I was saying, and when I was coming back into here.
Do me a favor, go to week 6, go to week 9/6/2021.
Okay.
Click on that. Go to the chapter 2 quiz. No, go to the chapter 2 practice. I'm sorry. Go to the chapter 2 practice.
Okay.
Click launch.
Yes, and I got launched to an assignment like this, which was McGraw. That's what I had. It had told me to begin, but that's what, now this is the other week. I'm still back a week. So I'm still trying to figure out what I completed from last week.
Okay, so go back to the following week. I'm sorry, go back to the following week.
No, okay, that's what I figured. I just wanted to make sure. So this one here.
Okay.
I completed one of these. I just don't know which one it was.
I know you did the Smart Book assignment. Click that chapter 1, major themes of anatomy and physiology, very top.
This one.
Yep. Click launch. Click begin. Just to do it, just to see what happens here.
Okay.
Okay, let's go back. Go back go back to Yeah, go back to that. Now click, now, Roberta, I'm sorry, Catherine, you don't see this. You're not going to see what we're doing here. Pretend you never saw it. Okay.
Oh, okay.
And the reason is because I want to see, Jade, click on your grades.
Oh, my grades. Okay.
And I'm doing this. It's a FERPA violation for Catherine to see
I
any
just
of
started,
this.
so I don't really mind. I don't mind
All
sharing
right.
it.
That's why. Okay. So if you look there, you have an empty score for the practice. That's why it's telling you need to do that.
Okay. Oh, nice. So I have.
Now go down. Go down.
Okay.
Go down. Do you see the chapter 1 quiz? You have a blank score there. So you need to do that.
So the chapter 1 quiz. And then the chapter 1 practice as well, correct?
Yes.
Okay, nice. Okay.
Does this help?
Oh, yes. No,
Okay,
yes.
good. Because see, I don't see what you see. And that's why I was like, I wanted to see what your screen was showing you.
Okay. No,
Okay.
I actually like that I can get to there like that. I didn't know that before. So
now let me tell you one more thing while we're playing with this.
Yes.
Every once in a while, do me a favor, go to Connect. Go back to McGraw-Hill Connect. Right, that I tab. Now click begin, just to click begin.
Okay.
Does it show you something else? Can you click exit assignment? Click exit assignment over here on the right side.
Oh, up here at the top.
Yeah, just click exit. Say yes, because you've already done this.
Okay.
Now click, it takes you right out of Connect, doesn't it?
Yeah. Yeah.
Can you go to MHE, go to McGraw-Hill, Google in McGraw-Hill. Catherine, you can come back if she wants to, when she wants to. Okay, click McGraw-Hill or click Connect, either one. So click Higher Ed. Yeah, that works too. Okay, now go scroll down. Click Connect there, log in. Put in your email and your password.
Okay, no, it was actually this one. I figured.
Sign in.
Yeah,
Okay.
that was sorry, hold on. No, I did create an account.
No, I understand more than I can say.
Yeah. Okay.
Now click our section. I'm not sure how. Click the down arrow there. Click. Do you see the down arrow by biology 121?
Oh yeah, that's down. Sorry, it came up. Yeah. It says.
Don't worry.
It's the book.
Can you click that down? Oh, I'm going to stop recording here. Bear with me.